Hello. While in the previous videos of Unit 7 we talked about bonding and how we could get a Lewis structure from the chemical formula, we never really made a strong connection between the orbitals that we see in an electron configuration and the actual bonding that takes place in the molecule. For the next couple of videos, we're going to look at two theories of chemical covalent bonding that will connect the atomic orbitals that we know to exist and the bonding and the geometries that we have seen in the molecules that we have studied so far. The two models are called valence bond theory and molecular orbital theory. Both have their advantages, and for this video I want to introduce valence bond theory. So I already jotted down a couple of bullet points concerning valence bond theory, the first of two theories that we are going to use to explain covalent bonding. The first bullet point is that in a covalent bond, atoms share electrons, and they are shared when atomic orbitals, such as the 1s, 2s, 2p, etc., of one atom overlaps with atomic orbitals of another atom. But before this bonding takes place, bullet point number 2, each orbital that will overlap must contain an unpaired electron. So in total, a bond would have 2 electrons being shared, one from each atom. And we've alluded to that in Lewis structures, but we never again really looked at specifically what orbitals are mixing. As a reminder, a single bond, the two atoms share 2 electrons. A double bond, 4 electrons. A triple bond, 6 electrons. Now still, those electrons are coming from an orbital, and each of the orbitals that are overlapping only contains 1 electron. So for instance, in a triple bond, there are 6 atomic orbitals mixing. They mix in pairs. Let me give you a couple examples of these types of bonds. Fluorine. So I am drawing the Lewis structure, and I am following the Lewis structure steps that we've discussed in previous videos. I just want to give right now examples of a double, single, and triple bond. Okay, but again, these still follow. You could have done this without understanding valence bond theory. It follows the Lewis structure rules, or the steps to draw these Lewis structures. The fourth bullet point is the formation of a bond results in a lower potential energy of the system. Okay, that will make a little more sense when we look at cartoons of how these atoms come together to make bonds. Why don't we look at the simplest case? The simplest is going to be using valence bond models or valence bond theory to make H2. So we are going to start now applying valence bond theory, and we're going to make H2. So if you look at each hydrogen atom, we know that its electron is in a 1s orbital. So here's our first hydrogen, and the s orbital is spherical. We can also get this from what? From the electron configuration. And then we're going to add another hydrogen. So do you see how each orbital has 1 electron? So they are unpaired. And then when you put them together, a bond is going to be 2 electrons. And you can show the overlap like this. And put the 2 electrons anywhere within those 2 spheres. Okay? That's the bond. And that is a covalent bond. And you could indicate it like that with a line. You know, this is a non-covalent, non-polar covalent bond. Now, what else do I want to say? Oh, this bond has a special name, and let me tell you what a sigma bond is. So sigma, or the symbol for sigma, is like that. That equals a bond where the bonding electrons, these two electrons here, are, how should I say this, are mainly along the bond axis. Okay? Meaning that we have two nuclei. We have a nuclei for the hydrogen on the left, a nuclei, what I keep saying nuclei, a nucleus for the hydrogen on the right, and that nuclei is in the center of this s orbital. So the axis made by the nuclei is right down there. Now, yeah, I drew two electrons and they're both above this dotted line, but in general, a sigma bond is when the two bonding electrons are near this axis, on or along this bond axis. That may sound a little strange, like how else can there be a bond? But there are actual bonds where electrons mainly exist away from the bond axis. Those are called pi bonds, and we're not going to look at that right now because, well, actually, let me write that down just as a comparison. Pi bonds are outside the bond axis. Okay. And they occur in double and triple bonds. So in this video, we're not going to look at double and triple bonds. We're mainly concerned about sigma bonds or single bonds. All single bonds are going to be sigma bonds. That's another rule of thumb you could have. Okay, don't worry about that. Ultimately, we could describe the bond, or we could even describe this bond right here, this one right there, as a sigma bond that is formed by the mixing of an H atom 1s orbital with another H atom and its 1s orbital. So that there are different notations to do this, but that to me indicates how is this bond being made. It's the overlap between two 1s orbitals from two different hydrogens. We're going to look at some more examples, but before I do that, I want to talk about the energies of this interaction, this bonding. We know that, actually let me, it's on the clipboard. You should be aware that you have to add energy to break a bond. But the opposite of that is when you make a bond, you release energy. One's making and one's breaking. So when you make a bond, energy is released. Let's first take a look at the figure on the left. Why does a bond even take place? A bond takes place because there's attraction between the nuclei of the two atoms and the electrons that are existing in between those two nuclei, right? Opposites attract. So here we have the arrows going to each other. But if opposites attract, how come this, it looks like this is hydrogen, how come this H bond doesn't go all the way and collapse upon itself? How come it doesn't get really, really close like here? That's because you have a balancing force, which is like charges repel, or we see repulsion right here. Even the electrons repulse each other. So there's a balance between attraction and repulsion between the electrons and the nuclei. And so there's a minimum in terms of energy. And you want to find the minimum of energy, the minimum of the energy, because that represents the most stable situation. Stable. So here we have two hydrogen atoms very far apart, and there's no interaction between them. They're very, very far apart, and there is no energy associated with those two atoms. They are separated. But as we get closer, do you see how we release energy? So when you go down, you release energy. And we get a minimum, like I said here, which is the most stable. In this case, the minimum occurs around 74 picometers. That is 74. A pico is 10 to the minus 12 meters. Okay. But if you push these any closer, okay, then the most stable situation, then you start to get this repulsion and the energy shoots up. Okay, and you're going to get to a point where it's impossible. The two atoms are going to be right on top of each other, and that's not possible. So we have a minimum. And all covalent bonds go through this kind of curve where it finds its minimum energy. That's all I need to say about those two figures. Why don't we go back and look at a more complicated example? And we're still going to use valence bond theory. And to use valence bond theory, we need to know where the electrons are, which orbitals, and where are they unpaired, right? Before bonding, each orbital will overlap. That overlaps must have an unpaired electron. Let's do F2. So F2, we have to visualize each individual atom and find the orbitals that have only one electron. It's going to be a valence orbital, okay? It's going to be the valence electrons that are involved in bonding. So let's take a look at the electron configuration for F. F is, do you have your periodic table somewhere? Yep. F has 9 electrons, but how many valence? 1, 2, 3, 4, 5, 6, 7 valence electrons. But let's do the whole electron configuration. 9 electrons, 1s2, 2s2, 2p5. Okay. And again, practice your electron configurations, 2p, 1, 2, 3, 4, and 5. But what we really need is the orbital diagram, not the electron configuration. So we'll do it for we'll do it for everything, actually. 1s, the 2s, and remember, there are 3p orbitals, okay, per energy level. So 1, 2, 3, and these are the 2p's. Okay. We have 9 electrons. 1, 2, 3, 4, 5, 6, 7, right? Using Hund's rule. 8, 9. See, there is your half-filled orbital. That is going to be involved in bonding. This is your unpaired electron that we were looking for bullet point number 2. So we have 2 fluorines and they're going to come together. Let me draw a fluorine here, okay, F, and I'm going to draw the valence orbitals, the orbitals that are in the valence shell, which is the 2 shell in this case. Yes, we have a 2s orbital, and it has its 2 electrons, and you can put them anywhere within that sphere. I like to draw my p orbitals with a red pen. I like to color code my orbitals, and remember the 3 p orbitals? They are all perpendicular to each other, and they are lobes. So this is 1 p orbital, like that. And I usually call them px, py, and pz based on the direction. We'll call this what is this? We'll call this the y direction, py. And I'm going to make this the one that has 2 electrons, so we'll call this the y. It really doesn't matter what you call y, x, and z. They're all 90 degrees to each other. They're all perpendicular. There's one in and out of the plane. Into the plane of the paper, out of the plane of the paper. And I'm going to put also 2 electrons. It doesn't matter if you put the 2 electrons in the same lobe or in different lobes. Just know that you can only put 2 electrons maximum in each p orbital. So we haven't taken care of this one. Oh, what do we call this? We'll call this the p z. We didn't talk about this orbital yet, the one that has a single electron. That we'll call the px. Okay, so it's a little crowded, but this is the electron we're most interested in. And actually, that's the orbital that's going to be overlapping with the other fluorine. So do you see how now we're making a bond? And that fluorine's px orbital has a single electron. There's your bond right there. There's your bond right there. But it's the same type of fluorine, right? You still have the 2s. You still have the other p orbitals, one going up and down, one going out and in. And let me just simplify this. 2 electrons there and 2 electrons there. But do you see, there's your sigma bond. Because you know that F2 Lewis structure looks like this. So, if I ask what atomic orbitals are making that bond, you could say that this bond is a sigma bond. Okay, look how the electrons are within or along the axis. It's called the bonding axis. Okay, right in between. So that's a sigma bond, and it's between a fluorine atom's p orbital. Now, some textbooks say 2p to specify second shell. Yeah, maybe I'll do that. See, I specified the shell here, the 1s shell for the hydrogen. So we'll say it's a 2p. Do I necessarily have to say it's a 2px? We're going to leave that off the notation. Okay, it's a fluorine 2p orbital with a fluorine another 2p orbital. So it's not the 2s orbitals that are mixing because they are not half filled, right? You have to use the orbitals that are half filled, and that is F2. Okay, there's one last thing I want to talk about for this introduction to valence bond theory, and it has to deal with shape. Let's take the example. Oh, by the way, I wanted to mention this. You know what this reminds me of? This reminds me of a ski slope. Where is the skier has the most potential energy on a ski slope? Is it at the top of the hill or in the valley? The skier has the most potential energy at the top of the hill. It's very high energy. It's very energetic. Okay, and it could convert that energy into, in terms of the skier, kinetic energy. But down here, the skier is very stable. In the valley, there's very little chance for it to move naturally because it's not going to move spontaneously uphill. So we could think of all of these reaction coordinates, not reaction coordinates, but these potential energy diagrams as a ski slope. That's all I want to say about that. Now let me talk about one more molecule, H2S. Okay. Based on VESPR, valence shell electron pair repulsion theory, we look at the Lewis structure and notice it has 4 balloons. We're still going to talk about balloons like we have in the previous videos. And 4 balloons are separated best by 109.5 degrees. 4 balloons is synonymous, right, with tetrahedral. Now we know that the molecular geometry is based off of the atom. So the molecular geometry is bent by the shape made by the 4 balloons, or the electron domains, right? Electron domain shape is tetrahedral. And the tetrahedral shape is synonymous with 109.5 degrees. Now, remember that I mentioned before that a lone pair will push harder against the bond. It's more repulsive. So it pushes the bonds a little bit closer than 109.5, and we would say it's less than 109.5 degrees. That's VSEPR theory. Remember I said that these theories, they have their advantages and disadvantages. For this particular molecule, VSEPR is not the best theory to use. You should be using valence bond theory. Because what does valence bond theory predict the bond angle to be? For valence bond theory, you have a sulfur, and that sulfur's electron configuration is what? It's 1s2, 2s2, 2p, 4. 1, 2, 3, 4, sulfur. 2p4. And then if we look at what potentially could be the orbitals that are half filled, I'll just do the 2p ones. 1, 2, 3, 4. So we have 2 that are half filled. Two available for bonding. So my sulfur is here, and they are p orbitals. They're p orbitals. I'm still going to draw all 3 p orbitals. Okay. And I want to pick 2 of them to be singly filled. I haven't picked those yet. Let me pick actually this one on top, okay, half filled, 1 electron, and this one to the left, right there. So this p orbital here is doubly filled, and that's looks like the one that's in and out. We haven't put any electrons there yet. So again, don't get confused. What you see there, that is not 2 half-filled lobes. Okay, that is a filled orbital. There are 2 electrons in that orbital. So no bonding can take place with this orbital. It already has 2 electrons. But that orbital can participate in bonding, and that orbital can participate in bonding. See how there's only 1 electron per orbital. So when we bring the hydrogen here, there's your bond, sigma bond between the hydrogen and the sulfur, 2 electrons. And here we have the second hydrogen, 2 electrons. That's H2S. Looking at the cartoon of the orbitals. The thing is, I said before that the p orbitals are all perpendicular to each other. That's a right angle. This is 90 degrees. So it's not 109.5. It's not even slightly less than 109.5. It's 90 degrees. In real life, when they do measurements, H2S has a bond angle equal to 92 degrees. So it's more close to the valence bond theory than it is to VSEPR. And is that all I need to say about that? Okay. So again, the real life H2S has an angle that's more predicted by valence bond theory than VSEPR. And I think this is basically the same drawing, okay? But it's a cleaner illustration. But S is in the middle, right? And you have the 2 hydrogens, and that is 90 degrees. Those are sigma bonds, okay? And it looks like this, right? H, H, no. Wait, how many lone pairs are there? There are 2 lone pairs. Okay. Don't forget, right? Don't forget that we have a 2s that has 2 electrons. Okay. Okay. So that's that. I just want to assure you that we are going to learn another type of theory called molecular theory or molecular orbital theory. Now, there are some molecules that follow VSEPR very well in terms of their bond angles. There are some molecules that follow valence bond theory very well in terms of their bond angles. In the next video, we are going to mesh these two. So in the next video, we are going to combine, or how about this? We'll say we'll mesh the two, and we'll use valence bond theory, and we're going to see molecules that use valence bond theory, spelling, that follow VSEPR rules. And the vast majority of cases, that's going to be true. The valence bond theory, we're going to refine this a little bit, and the refined theory is going to help us match the real life to the orbital picture to VSEPR. Okay, but that is the next video.